Okay, so welcome everyone to another episode of the Reading Club. And in today's episode and in the next few episodes, we are going to cover the pre-solve rules for MIP solvers. Okay, so pre-solve is an important component of a MIP solver, right? As you might all know. And this year, or rather the 2024 MIP competition is going to be about this particular component, which is pre-solve. Right, so that's why we are going to spend a few weeks learning more about pre-solve rules and few weeks because I cannot really cover all the pre-solve reductions in just one video. Okay, so there are lots and lots of pre-solve rules and we are going to see some of the interesting ones. Okay, so particularly we are interested in this paper. Okay, so which is pre-solve reduction in mixed integer programming by Assetberg and other Gurobi people, right? So this was actually first we are actually reading an older version which was published in 2016. The newer version is kind of probably similar, not so different. I don't know, but why we are interested in this is because of this particular table. Okay, so here is the impact of disabling pre-solve. This is how they demonstrate the effect of pre-solve, overall pre-solve reduction. Okay, so they have about over 3,000 models, and they basically measure all these things, right? So how many of them reached the time limit and could not solve, how many of them were faster or slower, or what was the time ratio, what was the nodes ratio, and how many models were affected, and all those things, right? So the time for the affected models, everything, right? So now we take a look at all these models, which take the slower one of them takes at least 10 seconds to solve, right? So in that case, we see that it's a big difference, right? So if we disable the pre-solve, the default is when pre-solve was on. In that case, 16 of them reached the time limit. And if we disable the pre-solve, then about 500 of them are reaching the time limit. So we could not prove optimality for 500 of them. So this was all using Gurobi solver. Okay, the older version, I think 6.5, and a lot of models are sometimes it is faster to disable pre-solve, but most of the time it is slower. Uh, and the overall time ratio is 9.05. That basically means that if the default version takes 1 second to solve, the if we disable the pre-solve, it will take 9 seconds to solve, right? So it is 9 times slower than the default version. And if we look at even the harder instances, which take 100 or 1,000 seconds, then this ratios are even bigger, like 12 times slower or 19 times slower, right? So that's a big impact in terms of solving time. Even if you look at the easier instances, right? So uh, for for most all instances, we see that it's like 3 times slower. But if you take a look at something that took slightly more than 0 second or 1 second, then it's still like kind of slower, right? So pre-solve is basically like it will bump up your solver speed if you do it properly, right? So nodes also, like if you compare the number of nodes explored by the branch and bound tree, then without pre-solve it explores twice or sometimes like 2.5 times more nodes than with than the version where we have the pre-solve enabled. Okay, so a lot of models are affected, and if we only focus on the times for the affected models, it's kind of similar, not so different. So overall, the point is that pre-solve is important component, and they mentioned basically two components, right? So pre-solve and cuts somewhere here. So that's why we are going to study pre-solve rules, right? So it's a very long paper. You can see it's 70 pages, right? So they cover lots of pre-solve rules, starting with pre-solve rules that are only affecting that are basically only considering one constraint at a time, or multiple constraints at a time, one variable at a time, multiple variables at a time, a lot of things basically, right? So we are going to like explore this paper in multiple videos. So this is like the first part of this video, and I'm going to start with pre-solve reductions, which only focus on one constraint at a time. Okay, so let's get started. Okay, so let's start with some notations. We'll quickly cover them, right? So we have minimize, some objective, ax, b, and some relation, right? So it can be less than equal to, or greater equal to, and x is between some bounds. Okay, so that's our problem, and some of these x are integer. Okay, precisely these are the integer variables set. Okay, so we will have rows and columns, right? So this is constraint matrix A, this is ith row, and this is jth column. And if I want to particularly look at ith row and jth column, then I will have the coefficient by this aij, and we can look at the ith row, but for certain specific subset of variables, then I can basically say something like this. Okay, so that's ith row, but not on all variables. We are only looking at the coefficients of variables that are in this particular set S. Okay, so that's rows and columns, and I'll introduce something that I missed if I need them. Okay, so next we want to cover some more notations. Okay, so we have first of all support for AI, let's say ith row, right? So what is this? It's basically a set of all the indices, right? So I in all the indices, all the variables. This is the set of all variables in our problem, such that their coefficient in the ith row is not 0. Okay, so that's the support of the ith row. You can define the support for the columns also, but you get the idea, right? So wherever the coefficients are non-zero for that row. Next we want to look at infimum of ith row and x. Okay, so what is this? Right, so this is basically like the smallest value that the row can take. And how do we find out the smallest value that the row can take? So there are two types of coefficients, right? So there are positive coefficients and negative coefficients. So let's say we have coefficients, right, where these people are positive, right? So what do we want these variables to do? So this variable, we are looking for the smallest value. So this we can get it by putting the variables at the lower bound. Now they might not be feasible, but this is like one. Assume that there is only one constraint in our model, then this is what this is how we attained our lower bound. Okay, and let's say if we have some coefficient which this part is negative, right? So for that we can get it by putting our variables to their upper bound. Okay, so this is infimum, and similarly you can also find out the supremum, right? So supremum is the highest possible value that this row can take. Is precisely the same thing, but instead of lower bound we have upper bound here, and here we have lower bound, right? So this is the largest value that this row can take, the left hand side part, and this is the smallest value that row can take. Okay, so we are going to keep this part over here all the time, just so we need to reference it. So first let's start with the first Presolve reduction. Okay, so let's say that we have our feasibility threshold, which is epsilon, and some notion of infinity. Okay, so we'll consider this as practical value of infinity. That's what they consider for Gurobi, right? So let's say our constraint is simple, right? So aix is, let's say, less than equal to bi. Okay, so what all things we can do using just this information: infimum, supremum, and support, right? So first of all, we can measure the supremum part, right? So what is the largest value this part can take? That's the supremum, right? So let's say if the supremum of aix is already less than equal to bi, then what does that mean? that means that our constraint is always satisfied, right? So we can even put additional epsilon here because that's our feasibility threshold. So even if it is, you know, slightly larger than bi, but it is less than equal to bi plus epsilon, then still we will consider that as a satisfied constraint. In this case, we can just simply remove this constraint. Okay, so that's one part, and you can basically do this for other types of constraints also, right? So this constraints or even equality constraints, then you have to basically measure that infimum and supremum are both within plus or minus epsilon range of this bi, and if that happens, then you can discard it. Same thing, right? So this is like satisfied constraint. We can just simply remove them from the model, and let's say if we measure the infimum, okay, so the smallest value that this part can take, and let's say this part is strictly greater than bi plus epsilon, then what does that mean? So we want that to be taking smaller values than bi, but if the smallest value that this constraint can take is already bigger than bi, right? So that means that this model is infeasible. This constraint will never be satisfied, right? So we can just simply call that entire model as infeasible, and we don't even need to solve the rest of the problem. Okay, so this is like very basic stuff, and what else? We can also reduce some coefficients, right? So this is redundancy removal and cleanup, right? So cleanup, what we can do, let's say if some coefficient is like very small, let's say if the kth variable's coefficient, let's say it is 10 raised to minus 3, less than 10 raised to minus 3, the absolute value is very small, and there are more criteria for, you know, calling something small, this, and the coefficient times its activity for that variable, right? So it's upper bound for that variable minus lower bound for that variable, this times the size of the support, the number of all non-zeros in this row, this entire quantity, if this is less than 10 raised to minus 2, then we can set this coefficient to 0. Okay, so what do we mean? So basically it's like simply you know, various ways of saying that this is just too small to make an overall effect in this constraint. So we can just simply set this to 0, put the variable, like, I mean, for this constraint we can just set the variable to its lower bound and subtract the lower bound from bi, right? And we can just keep removing you know, smaller coefficients like this, so that our model will become sparser and it will become easier to solve later on, right? So that's redundancy removal and cleanup. Okay, so next we are going to take a look at bound strengthening. Okay, so let's say our constraint is aix less than equal to bi, and let's break this down into two parts. Okay, so first I will consider this set S and one individual coefficient for the kth variable. Okay, so all this is basically all the non-zeros except k, and this is the kth variable is less than equal to bi, and let's say we are only interested in getting a better bound for this xk variable, right? So what we can do is we can find some lower bound on this part, right? So as long as we are looking at just one constraint at a time, we can simply use its infimum, right? So what we can do is let's say ls, the lower bound for this set S, is basically infimum of ais xs, right? So this is the smallest value that this can take. So we can basically move this to the other side and subtract it, right? So we can say that aik xk is less than equal to bi minus ais xs, and if we replace this by its lower bound, this inequality still holds, minus ls, right, this part, and then we just simply divide it by aik, right? It's as simple as that. So this is my new upper bound for this variable xk, and if it is less than my current upper bound, then I can use this one and discard this one, right? So that's simple. Similarly, like if so this is like if aik, this part is greater than 0, right? So if it is less than 0, then this inequality will change the sign and it will become greater equal to, and it will be, we'll get a new upper bound for new lower bound for our variable xk, right? So that's the simple way of finding better bounds. So if these bounds are very relaxed, then we can find tighter bounds using individual constraints, one constraint at a time, and it's kind of simple. And you can do even further, like if this, we know that if this variable is integer, then for the upper bound we can use the floor function, right? So the smallest integer below this value, and if it is the lower bound, then we can use the ceil function, right? So that's how we find the better bounds for individual variables using one constraint at a time, and we can just keep doing this for a while, right? So we tighten bound for one variable, that will lead to bound changes in some other constraint, because like this part can change, its infimum can change, because look at this infimum basically depends on its lower and upper bound, right? So this parts can keep changing, and once we change the bound of one variable, it will affect the bounds of other variables in other constraints, and so on and so forth, right? So we can just keep doing this, but Gurobi said that they basically do it only once for each constraint in one pre-solve pass, okay? And there is a reason behind that, because like there are cases in which if they keep doing bound propagation like this, then it will lead them to an infinite loop, so they limit it. And they also like change the bound only if it is like improving by a certain margin, right? So just because it's slightly better, they don't just improve it. It has to be at least better by a certain threshold, and if that threshold is not met, then they just don't consider this new bound. Okay, so that's bound strengthening. Okay, so far we looked at bound strengthening. Okay, so now we are going to look at coefficient strengthening, but before that we need to cover some definition. Okay, so we'll call something called dominated constraint, right? So let's say we have first constraint, which is ax less than or equal to b, and the second constraint a prime x less than or equal to b prime, right? So we'll say that this constraint dominates this constraint. When can we say that? So let's say that the feasibility region for this constraint is f, and for this constraint is say f prime. Now if f is a subset of f prime, then we can say that this constraint dominates this constraint, right? So if we have two constraints like this, and if we know that the feasible region for this top constraint is a subset of feasible region of this bottom constraint, then we can remove this bottom constraint completely and just only keep this first constraint, right? So that's what we'll be using to strengthen the coefficient. Okay, so let's again consider the constraint that we have been looking at, right? So xs plus aik xk is less than or equal to bi. Okay, so previously we strengthened the bounds of this variable xk, right, using infimum and supremum and all those information, and now we want to change this information aik, right? So we want to find a new constraint which is tighter constraint, so that we can remove this original constraint. So we have, let's say, this constraint, and we want to find something like this, for which the feasible region is a strict subset of this feasible region of this constraint. Okay, so also now for now assume that, so like if it is a linear variable, a linear constraint with all variables are continuous, then I don't think we can do much. But let's say if this variable is integer variable, right? So this is in z. Okay, this is an integer variable. Let's say its upper bound is uk, right? So that's what we have been using as upper bound for now, and let's see if we can tighten the coefficient for this constraint. Okay, so let's find out the supremum of this part. Okay, so let's say that uis is basically the supremum of AIS XS. Okay, so this is the supremum of it. And let's say what happens if this variable takes one value less than its upper bound, right? So let's focus on UK minus 1. Let's say this variable xk is taking the value UK minus 1. Let's see what happens, right? So this part will be as it is. We'll say that AIS XS plus AIK, this part is UK minus 1 is less than equal to BI. Okay, and let's move everything to the right hand side. Okay, actually now let's keep them here and let's replace this part by its supremum. So we want to find out if this constraint is already satisfied when xk is taking this value, particular value UK minus 1. So when will this constraint be already satisfied? So this part is constant, this part is constant, only variable part is over here, and let's find out, and this is like an upper bound on this variable part, right? So if the supremum of this part, which is UIS, is already less than equal to BI minus this term AIK times UK minus 1, in that case this constraint will already be satisfied, right? So in other words, we have 0 less than equal to BI minus AIK times UK minus 1 minus UIS, right? So this part, right, if it is greater or equal to 0, then this constraint is already satisfied, right? So all of these parts are kind of known to us, right? So UIS we can find out using the supremum, AIK we know that, UK we know the upper bound of variable xk, BI is here. So if this entire quantity is greater or equal to 0, then this constraint is already satisfied. And let's get crazy, right? So let's say that this is strictly greater than 0, right? So this part, let's actually call this part, this entire part, D, right? So D is equal to this part, right? So if this D value is strictly greater than 0, right, then this constraint will always be satisfied as long as xk is taking UK minus 1 or lower values, right? Let's not talk about lower values, but if it is taking UK minus 1, then it is already satisfied. So by how much it is satisfied? By this D value, right? So we have this D portion extra that is helping us with this bound. So using this information, we want to find another coefficient for xk which is better than this one, and correspondingly we'll modify the right hand side as well, right? So let's consider this particular constraint, AIS XS plus, instead of using AIK, we are going to use AIK minus D. Okay, this is my coefficient of xk, and right hand side I am going to modify by BI minus D times UK, right? So this is a completely different constraint, right? It has a different coefficient of for xk, and it has a different right hand side than this one, and the claim is that this particular constraint dominates this constraint, right? So it has a stronger relaxation, right? So the feasible region for this constraint is F, which is a subset of feasible region for this constraint. Okay, so let's see how that works. So let's consider the value UK, right? So for this UK value, right, so what happens? So xk will take UK, so here it will be, this part is the same in both constraints. Here it will be AIK UK is less than equal to BI. So here it will be like this part is same, AIK UK minus D times UK, right? So that's minus D times UK is the extra part, and here also we have minus D times UK, so they are both same, right? So both of them will be basically like the same constraint for xk equal to UK. Okay, and now what happens for xk equal to UK minus 1? So for xk equal to UK minus 1, what happens to this constraint? So this constraint basically will will have like similar things that we did here, right? So let's talk about, let's call this number 1, let's call this constraint number 2. Let's say what happens for constraint number 1. Okay, so we have AIS XS plus AIK times UK minus 1 less than equal to BI, right? So this part is constant, this part is constant. We can put this to the right hand side, right? So what will happen is AIS XS is less than equal to BI minus AIK times UK minus 1, right? So what is this part? So this entire quantity, right, is D, right? So we can just write down over here is equal to D. So using this we can find replace these two terms, BIK minus AIK UK minus 1 is equal to D plus UIS, right? So this part is same as saying that this is equal to UIS plus D, right? So the bound for this part AIS XS is UIS, right? And over here we have less than equal to, and this is UIS plus D, and we say that D is strictly greater than 0, right? So that means this constraint is trivially satisfied, and this bound is kind of a little bit weak, right? So it should be ideally UIS, but it has UIS plus D. That's why we basically talk about this strengthening this constraint. Whereas if you find a similar way, the substitute xk over here, xk value of xk as UK minus 1, then you can find that for using the same substitution, like if you just simplify these terms, right? So let's actually do that. For number 2 we have AIS XS, right, minus DUK. Okay, let's actually do that, right? Plus AIK minus D, and here it is UK minus 1 is less than equal to BI minus DUK. Okay, so let's split this part, right? So this part is AIK times UK minus 1 minus DUK plus D. Okay, and this part is BI minus DUK. So this part and this part cancels out. Okay, and what happens to these other parts, right? So what is equal to, we can basically like substitute the value of D over here, or we can just take this part on the other side, which will become so this term will be AIS XS plus, let's just take this term over to that side, so it will become this, which is UIS plus D, and we keep the D part over here as it is, so this will become on the other side UIS plus D, right? So this is basically the same term, right? AIK times UK minus 1, which is subtracted from BI from the right hand side, so which we saw that it is UIS plus D, so this is UIS plus D, and this D parts will cancel out. So this term AIS plus AIS XS has its tighter bound, which is UIS, which is the good part, right? So this is what we want. And for all the smaller values for xk, both of these constraints are kind of trivially satisfied, right? So that's because this D is already greater than 0, right? So for xk equal to UK minus 1, it was satisfied. So for smaller values also it will keep satisfying. Okay, so the smaller values it will take, so this subtracted part will be even smaller, so that's why this part will keep staying greater or equal to 0, right? So all feasible values for this constraint 1 are also feasible for constraint 2, but there are feasible values for constraint 1 which are not feasible for constraint 2, right? So this constraint 2, right, it's we just proved this part, right? So its feasible region is a subset of the feasible region of this constraint, right? So this is the strengthening of coefficient. It's kind of a bit involved, but the idea is very simple, right? So what you need to do to find this kind of substitution is first of all find out this value d using the uk minus 1 value of xk. And if this d is strictly greater than 0, and if aik, this coefficient, is strictly bigger than d, is greater or equal to d, then you can change this aik to aik minus d, and correspondingly for the right hand side you can change bi to bi minus duk, right? So this is the coefficient strengthening, and that can also have a lot of effect. Okay, so far we are talking about the Presolve reduction, and in this part we covered three things, right? So one is cleanup, number two is bound strengthening, and number three is coefficient strengthening, right? So this is all looking at one constraint at a time, right? So next we will see some more of these rules which still look at one constraint at a time. In the next parts we will also look at multiple constraints at a time, and then we'll look at one variable at a time and multiple variable at a time, and entire model and all those things, right? So all those things there are basically lots of Presolve reductions, and for this video it's already kind of bit long, so I covered these three parts. Okay, so we'll continue reading this paper and covering more parts of this part, one constraint at a time, and then m constraint, multiple constraint at a time in later videos, right? So this parts will take some time, but yeah, so that's the goal. Like, we will cover this entire paper, and we'll go through this part, and this parts also in the future weeks. So stay tuned. If you like this, then hit the like button, use the subscribe button, all those things what normal people do, and see you in the next video. Bye.